Hello students, today we will discuss torque acting on dipole, that is very first question of assignment 5.2, and using it we will derive expression for frequency and time period of oscillation for any magnetic dipole placed in external magnetic field. In next session we'll talk about magnetic potential energy, and then we'll have Gauss's law for magnetic field. So let us start with the seventh question of today's assignment 5.2. This topic is very similar to the one we had in electrostatics. In electrostatics, we did derive expression for torque acting on electric dipole. So suppose if you have electric field like this, and in this electric field if you have to place an electric dipole say at an angle theta, what do? We assume that the angle is theta, length is say 2a, and then we look at the force acting on positive charge. If it is plus QE, force acting on negative charge will also be QE but in opposite direction, so minus QE. And then we talk about the torque due to force on positive charge, torque due to force on negative charge. So we take A cross F positive plus A cross F negative. Substitute values, simplify, and ultimately you will end up with P cross A. Now in case of magnetostatics, you have magnetic dipole moment and magnetic field, but logic remains same. So here if I consider magnetic field to be in this direction, now how do you produce magnetic field to be in this direction? So you will have to have north pole placed here and south pole in the right side, and then let me assume that this is the magnetic dipole. Magnetic dipole is nothing but a bar magnet. So if this is north pole, if this is south pole, I can say that this is the direction of magnetic dipole moment, that is from south to north. Let the length be L, so this will be minus L and this will be plus L, so total length will be 2L, and we assume that this angle is theta, angle between B and M. M is magnetic dipole moment. So how much is the force acting on the north pole? Force acting on the north pole, if I denote it as F1, it is MB. What is M? What is this M? It is pole strength. Okay. And what is the force acting on south pole? It is also MB but in opposite direction. Let it be F2. Now, as the two forces are equal and opposite, F1 and F2 both are same magnitude wise, but direction wise they are opposite. So, the resultant force on the magnet or magnetic dipole will be 0. But as the two are having different lines of action, see, first one is acting along this line, second one is acting along this line. So there is gap between the two. How much is the perpendicular distance? If the angle is theta, perpendicular distance is 2L sine theta. So we can find out torque acting. Now how to determine torque acting on the dipole? So torque is just like previous case, L cross F1 plus L cross F2. Now in second case the direction will be opposite, so minus L will take, and then we have L MB sine theta plus L MB sine theta. See, corresponding to this negative sign we have this force value also negative, so ultimately we end up with positive sign. So what is the torque? Torque now is 2 Lmb sine theta. But 2L into M, that is pole strength into separation, and that is nothing but dipole moment, and hence it becomes mb sine theta. Or else I can write this as m cross b. So that is the torque acting on the magnetic dipole, which is very similar to what we had earlier in electrostatics. Compare the two. Now, if I consider the torque as I alpha, earlier in 11th standard you must have studied the way we have F is equal to m in Newton's second law. In the rotational motion, your torque is equal to I alpha. What is I? Moment of inertia. So we denote it with Im. We can write this as Im d2 theta by dt square, isn't it? So now I use this formula for small angle. When angle is small, this formula mb sine theta can be written as mb theta. Moreover, when you have rotation in this manner, when you are rotating the dipole in anti-clockwise manner, the tendency of the torque is to get dipole back. So when theta is anti-clockwise, torque is clockwise. So the two are always opposite, and hence we consider negative sign here. So left side is replaced with Im d2 theta by dt square is equal to minus mb theta. Can also be written as d2 theta by dt square plus mb by Im into theta is equal to 0. Isn't it similar to one of the earlier equation d2y by dt square plus omega square y is equal to 0. We had similar equation in topic of simple harmonic motion. So comparing the two, we realize that this omega square is nothing but mb by Im. So omega square is mb by Im, or else I can write omega as root mb by Im. What is omega? Omega is angular frequency. So 2 pi f is equal to root mb by Im, or else I can say that frequency f is equal to 1 by 2 pi root mb by Im. And if I want time period, I can take inverse of this. So 2 pi under root Im by mb is formula for time period. So we have formula for time period and we have formula for frequency both. So if the answer, suppose the f value is 1 hertz, what does it mean? It means that when you place the dipole in magnetic field and when you allow it to oscillate, the dipole will oscillate. The dipole. So if this is my magnetic field and if this is how dipole is initially placed, this is the most comfortable situation for the dipole with north pole here and south pole here. Suppose from this situation, if you take dipole in this orientation, what the dipole will do? Dipole will try to come back to this situation, but it will not be able to stop there. So it will go here. Again, from that point, it will go back. And again, it will reach here. So dipole will oscillate like this. Dipole will oscillate, and the frequency of oscillation is given by this formula. How fast or how many times dipole will oscillate per second, that is given by this formula. So that was the topic. Let us have a quick look at the answer. Consider A magnetic dipole with pole strength m and 2l, so magnetic dipole moment can be given as this. Earlier also we had seen this is the situation. Force acting on north pole, force acting on south pole, both are equal and opposite. Theta is the angle between magnetic field and dipole moment. M is dipole moment. So the force on north pole is mb, force on south pole is also mb but in opposite direction. So there should be negative sign. And then torque is r cross f. We know that torque is r cross f. So for north pole, what is the r value? For north pole, this is L, and for south pole it should be minus L. So with that we have torque acting on south pole, forces are equal, and this is the resultant torque. Torque due to force on north pole, torque due to force on south pole. And the two are added. As I said, this force on south pole is negative and position vector is also negative. Ultimately you will end up with positive result, and this is the torque. So M cross B is the torque acting on magnetic dipole when placed in external magnetic field. Then second question is derive expression for frequency and time period. So we start with this MB sine theta. From where we got this negative sign? Negative sign indicates the fact that this torque and this theta both are opposite in direction. So torque is replaced with I alpha. I is here mentioned as Im, and alpha is d omega by dt, or else you can write this as d2 theta by dt square. So with slide mass you will end up with this, which is very similar to second order differential equation of SHM. Compare, simplify, and this is the formula for time period, and from that you get formula for frequency. So that is all about torque acting on dipole and time period and frequency of oscillations of dipole placed in external magnetic field. Thank you.